Welcome to Topic 1903, Green Infrastructure for Urban Stormwater Control. This presentation introduces stormwater as an ecological planning issue rather than a narrow drainage problem. The aim is to show why urban runoff has become more severe in dense settlements, how green infrastructure changes hydrologic behavior, and what the Topic 1903 evidence files suggest about realistic performance. Across the lecture, we move from concepts to evidence and from evidence to planning workflow. The key idea is that planners should not treat green roofs, bioswales, rain gardens, or permeable paving as fashionable objects added at the end of a project. They should be understood as spatial interventions that affect storage, infiltration, timing, water quality, and urban resilience. By the end, you should be able to explain the ecological logic behind these measures, interpret them within climate adaptation policy, and evaluate how GIS, BIM, and scenario-based thinking can support defensible design decisions. The structure of the session is deliberate. We begin by defining the urban stormwater problem and explaining why runoff is shaped by land cover, form, and infrastructure condition. Then we introduce the main types of green infrastructure and the hydrologic processes they influence. After that, we examine evidence from the supplied case studies and publications, including green roof monitoring, watershed scale effects, and neighborhood planning models. The later slides focus on workflow, how planners can screen sites, compare strategies, coordinate design decisions, and account for trade-offs before detailed construction decisions are made. This sequence matters because performance percentages have little value if they are disconnected from planning scale, policy context, and maintenance reality. Topic 1903 is therefore not just about what works in theory, but about how to move from evidence to practical, context-sensitive intervention. It also helps learners understand why evidence has to be read in relation to scale, function, and implementation pathway rather than in isolation. The learning objectives frame the whole deck. First, you should be able to explain the basic concepts of ecological approaches in landscape planning. Second, you should be able to interpret climate adaptation policies and planning frameworks, including the broader European sustainability context. Third, you should be able to analyze ecological risks using digital tools such as GIS, BIM, and parametric design methods. Fourth, you should be able to outline nature-based solutions and multifunctional green infrastructure models. Fifth, you should be able to argue for interdisciplinary and inclusive ecological planning principles. The associated skills are equally important: integrating ecological networks into planning scenarios, developing adaptive strategies for climate-related risks, applying sustainable water management thinking, and strengthening the resilience of urban form. Topic 1903 therefore expects you to connect evidence, spatial reasoning, and professional judgment in a way that supports real planning and design practice. In assessment terms, you are expected to move from explanation to evaluation and from evaluation to justified planning choice. The first technical lesson is that urbanization changes how water moves. In undeveloped landscapes, rainfall is divided among infiltration, evapotranspiration, shallow storage, and slow overland flow. When surfaces are sealed with roofs, asphalt, concrete, and compacted ground, that balance shifts quickly. Water reaches drains faster, peak discharge increases, and the time between rainfall and flooding becomes shorter. Pollutants that settle on streets and hard surfaces are also washed downstream more efficiently. In many cities, this creates pressure on aging drainage systems, especially where combined sewers or undersized networks were not designed for current development intensity. The planning implication is important. Runoff should not be treated only as a pipe capacity issue. It is also a land use, design, and ecological function issue. Decisions about surface cover, storage opportunities, street form, open space, and building retrofits all influence resilience. Stormwater planning today is closely tied to climate adaptation and resilience policy. Instead of treating drainage as a hidden technical service, many frameworks now connect water management to biodiversity, public space, resource efficiency, and disaster risk reduction. Within the European policy context, that shift is visible in the broader sustainability agenda and in support for nature-based solutions as practical tools for adaptation. For Topic 1903, The policy lesson is that green infrastructure should not be introduced as decoration or branding. It has to be connected to measurable planning goals. That means linking site-scale measures to street, district, and watershed priorities, and showing how they contribute to both environmental quality and risk management. The policy perspective also prevents a common mistake, assuming that one intervention automatically solves every problem. In reality, resilience comes from coordinated systems, not isolated devices. That broader framing is useful because it links stormwater decisions to resilience funding, environmental justice, and long-term urban quality. At this point, we need a clear vocabulary. Green infrastructure is not a single technology. It is a family of measures with overlapping but distinct roles. Green roofs are useful where roof area is abundant and ground space is limited. Bioswales guide and filter runoff along linear routes, especially in streetscapes and parking edges. Rain gardens provide localized detention, filtration, and infiltration in planted basins. Permeable paving reduces sealing and can support distributed storage and infiltration where traffic and soil conditions allow. The planning challenge is to match each option to urban form, drainage pattern, and maintenance capacity. A dense commercial district may rely more heavily on roof retrofits and hardscape solutions, while a lower-density residential area may have more opportunities for rain gardens and swales. Good practice depends on building a coherent treatment train across scales. The same city may therefore require different measures in different neighborhoods, even when the overall stormwater problem appears similar on paper. It is often more useful to compare interventions by function than by name. Every green infrastructure option works by changing one or more hydrologic processes: capturing rainfall, storing it temporarily, slowing conveyance, filtering pollutants, allowing infiltration, supporting evapotranspiration, reusing water, or releasing water more safely over time. This process view helps planners understand why performance varies. A device that is excellent for small and frequent events may lose effectiveness in larger storms once its storage fills. A layout that improves water quality may not produce the lowest local flood depths. A system designed without maintenance access may gradually lose infiltration capacity or become clogged. Looking at function also supports better combinations of measures. For example, source control at the roof can be paired with street-level detention and neighborhood-scale conveyance improvements. Names alone do not tell you whether a measure suits a specific urban context. Thinking this way also makes it easier to explain trade-offs to decision-makers who may otherwise focus only on one metric or one visible technology. Green roofs deserve particular attention because they translate ecological planning into very dense urban form. A green roof is not simply a planted surface placed on top of a building. It is a layered assembly that combines vegetation, growing medium, filter layers, drainage components, and waterproofing to intercept rainfall and delay runoff at the source. In compact neighborhoods, that is valuable because roof area may be the largest available surface for intervention. Green roofs can also contribute to cooling, habitat support, and amenity, which makes them multifunctional rather than purely hydraulic. But this slide also carries an important caution. Green roofs are not universal substitutes for all other measures. Their performance depends on roof depth, vegetation type, antecedent moisture, storm pattern, and structural capacity. For most planners, they work best as strong source control measures coordinated with complementary systems at ground level. The evidence on green roofs is promising, but it needs to be interpreted carefully. In the Sheffield testbed, the monitored roof retained just over half of cumulative annual rainfall and reduced peak flow during significant events, showing that green roofs can provide real hydrologic benefits under operational conditions. Review literature supports similar conclusions about runoff reduction, attenuation of peak discharge, and longer runoff response times. However, the same evidence warns against simplistic claims. Performance varies across climates, rainfall patterns, substrate depth, and roof design. Pollutant behavior can also be complex, because some roofs improve quality while others may initially release nutrients depending on media and establishment conditions. The planning lesson is balanced. Green roofs can work, but they should be sized, justified, and communicated with local assumptions in mind. Topic 1903 also asks us to move beyond individual parcels. One of the supplied studies is important because it evaluates stormwater green infrastructure at watershed scale rather than only at device scale. That matters for planning, since urban outcomes depend on cumulative implementation and network effects. In the Mid-Atlantic case, watersheds with higher levels of green infrastructure implementation showed lower hydrologic flashiness and lower nitrogen export than watersheds with minimal implementation. That suggests distributed interventions can make a measurable difference at larger scales. At the same time, the results were not uniformly positive across every indicator. In that analysis, reductions in phosphorus and combined sewer overflows were not statistically significant. This is a useful teaching point. Watershed benefit is real, but it depends on the outcome being measured, the level of implementation, and the existing infrastructure context. It also suggests that the scale of implementation matters. Scattered devices may help locally, but broader spatial coverage is usually needed for system effects. Before detailed design, planners need an efficient way to compare options. The New York screening case is valuable because it demonstrates a practical first step. Rapid assessment of which measures deserve more detailed investigation in a specific watershed. In that low-density residential context, bioretention and rain gardens emerged as the strongest individual strategies for runoff reduction, while combinations of interventions produced larger overall reductions than single devices alone. The main lesson is methodological. Not every project should start with high-cost simulation. Early screening can identify the most plausible strategies based on land use, imperviousness, available space, and drainage structure. That saves time and focuses technical effort where it matters. It also supports better planning conversations, because stakeholders can compare relative suitability before becoming attached to a particular solution. Screen first, then move into detailed hydrologic, design, or cost analysis. In professional practice, that makes screening a bridge between broad policy ambition and site-specific intervention design. Neighborhood scale modeling adds another layer of insight because it reveals trade-offs among objectives. In the Chicago application, the model was intentionally parsimonious. It was designed to support fast scenario exploration rather than to function as a perfect predictive engine. That makes it very relevant to planners, who often need to test multiple options quickly in early project stages. In that case, bioswales performed slightly better overall than the other tested interventions for reducing flooding extent, downstream runoff, and pollution. Permeable pavers were also attractive where space limited the use of larger vegetated measures. Most importantly, layouts optimized for one objective did not always optimize another. A configuration that performed well for pollution reduction was not necessarily the one that minimized flooding most effectively. Performance goals must be declared before alternatives are ranked. This is why scenario planning is so valuable. It makes competing priorities visible before capital is committed. The learning outcomes explicitly mention GIS, and that makes sense because GIS is the most natural entry point for green infrastructure planning. It helps planners identify where runoff risk, impervious cover, drainage pathways, available space, and local constraints intersect. In practice, a GIS-led workflow might begin with mapping flood complaints, topography, land cover, drainage inlets, and ownership patterns. It can then be used to prioritize roofs with suitable area, streets with retrofit potential, or open spaces that could host detention and infiltration measures. Importantly, GIS should be presented honestly. Its strength in Topic 1903 is screening and prioritization, not false precision. It helps narrow down where interventions are plausible and where they are likely to be ineffective or infeasible. That makes GIS a bridge between ecological risk analysis and implementable design decisions. BIM and parametric design enter the workflow after screening has identified plausible sites and strategies. Their value lies in coordination and iteration. For example, a green roof retrofit can be tested against roof area, slope, drainage points, storage depth, access paths, loading constraints, and conflicts with existing equipment. Parametric rules can quickly generate alternative sections or layouts to see how changes in geometry affect storage and constructability. BIM can coordinate multiple disciplines so that waterproofing, planting systems, overflow routes, and maintenance access are not treated as afterthoughts. But Topic 1903 also requires a careful warning. These digital tools do not automatically validate hydrologic performance. They help structure design decisions, they do not replace local rainfall data, evidence from comparable systems, or a credible maintenance strategy. Used properly, they make design coordination stronger and more transparent. They are especially useful when retrofit projects involve several stakeholders and many technical constraints that must be reconciled quickly. A major strength of green infrastructure is that it supports circular and multifunctional thinking. Traditional drainage often treats stormwater as a nuisance to be removed as quickly as possible. Ecological planning asks a different question. Can rainfall be slowed, stored, reused, infiltrated, or reintroduced into local ecological cycles in ways that create additional value? When stormwater is approached as a resource, the planning conversation expands beyond flood control. The same intervention can contribute to cooling, habitat, amenity, shade, public space quality, and even water reuse in some contexts. This multifunctionality is one reason green infrastructure belongs in broader ecological planning rather than being confined to engineering alone. Still, multifunctionality should not become a vague slogan. Each claimed co-benefit needs to be appropriate to place and scale. In Topic 1903, circular water management is strongest when hydrologic function remains clear. It also strengthens the public argument for investment, because one project can support several urban policy objectives at the same time. A rigorous presentation also needs a limitations slide, because green infrastructure is not universally suitable or maintenance-free. Roof retrofits may be limited by structural capacity and access. Permeable systems can clog if sediments are not managed. Performance percentages often drop during large storms or under saturated antecedent conditions. Pollutant removal can vary by substrate, source area, and maintenance history. Ground-level systems may conflict with utilities, contaminated soils, or right-of-way constraints. Governance can be just as important as design, because unclear ownership or maintenance responsibility can weaken performance over time. This caution does not undermine green infrastructure. It makes the case stronger by preventing overselling. Topic 1903 teaches that the right message is conditional rather than absolute. Green infrastructure is powerful when matched to context, sized honestly, coordinated across scales, and supported by inspection and maintenance. Technical performance alone does not determine success. The final learning outcome emphasizes interdisciplinary and inclusive implementation, and that is especially relevant for visible public realm interventions such as rain gardens, bioswales, and neighborhood retrofit programs. Planners, engineers, owners, maintenance teams, and local communities all affect whether a measure is accepted, cared for, and sustained. Inclusion matters because risk and co-benefits are unevenly distributed across cities. If interventions are placed only where implementation is easiest, they may miss neighborhoods with the greatest vulnerability. Interdisciplinary practice matters because ecological, hydrologic, construction, and governance decisions are tightly linked. A strong Topic 1903 response therefore combines spatial evidence with collaboration and stewardship. Green infrastructure becomes more resilient when technical design, institutional responsibility, and local acceptance are aligned from the beginning. In that sense, implementation quality is partly a governance question, not only a design question. The Sheffield Green Roof Study is an especially useful best case because it is empirical, monitored over time, and directly relevant to source control planning. It shows that green roofs can retain a meaningful share of annual rainfall while also reducing peak discharge and altering runoff timing during significant events. Just as important, the study demonstrates why monitoring matters. Natural rainfall is irregular, and real roofs do not behave like simple textbook storage tanks. Performance depends on the pattern and sequence of storms as well as on the condition of the system. For planners, the transferable lesson is not that every green roof will reproduce the same percentages. The stronger lesson is that source control benefits are real when the system is well designed and when claims are interpreted in relation to climate, storm depth, and antecedent conditions. It is therefore a strong case for teaching realistic expectation setting alongside technical optimism. The second best case lesson comes from combining the screening and neighborhood modeling studies into a practical workflow. Together, they show how planners can move from a broad comparison of options to more tailored scenario testing. The first step is to use local land use and drainage conditions to identify which interventions are most plausible. The second step is to define the primary objective clearly. Are you trying to reduce flooding extent, reduce downstream runoff, improve water quality, or balance several goals? The third step is to test layouts and combinations rather than assuming that one device will dominate everywhere. This is a powerful professional model because it avoids both extremes, jumping too quickly into detailed design, or staying forever at the level of abstract policy language. Evidence-based screening, clear objectives, and scenario comparison allow green infrastructure to be used as a planning system rather than as a collection of pilot projects. To conclude, urban stormwater should be understood as an ecological planning problem shaped by land cover, policy, infrastructure capacity, and social choice. Green infrastructure works because it captures, stores, slows, filters, reuses, or more safely releases water. Measures such as green roofs, bioswales, rain gardens, and permeable paving each have advantages, but none should be treated as universally superior. The topic 1903 evidence base supports meaningful hydrologic benefits, especially for source control and for cumulative watershed improvement, while also highlighting trade-offs, constraints, and maintenance needs. That is why the best professional mindset is iterative rather than promotional. Start with screening, clarify your performance objective, test combinations, coordinate design carefully, and build in maintenance and monitoring from the outset. When these conditions are met, green infrastructure becomes a credible and multifunctional strategy for climate adaptation and urban resilience. That is the core ecological planning message of topic 1903. Multifunctional systems perform best when they are place-based, evidence-led, and maintainable.